Unit 7, Semester 4, Biomolecules. Biomolecules. Biomolecules are the compounds, organic compounds, mainly related to living organisms. For example, carbohydrates, proteins, enzymes, vitamins, hormones, nucleic acids, etc. Living organism is made up of organs. Organs are made up of tissues. Tissues having cells, and cells are made up of organelles, and these are biomolecules. Well, sun is the source of energy, which gives us radiant energy. This radiant energy is used for photosynthesis in plants. So this way, photosynthesis produces starch and oxygen with the help of sun energy. And this way, this starch and oxygen is required by animals. So that will be transformed to animals, and that is chemical energy for animals. Photosynthesis. It is a photochemical process possible in presence of sunlight with the help of chlorophyll. CO2 is absorbed from atmosphere, water from the ground, and trees will carry this reaction, and they will produce glucose plus oxygen. The solar energy is stored in plant kingdom due to photosynthesis. Plants are thus primary source of energy for animals and humans. Well, respiration occurs in living beings, which is this one, where plants are eaten by animals and humans, and they will get glucose. This glucose is combusted in presence of oxygen, produce CO2 and H2O, and this energy is used for living. Carbohydrate. The compound contain carbon and water are known as carbohydrates. Their common formula will be CX, H2OX or CnH2ON. Carbohydrates are also known as saccharides. Classification of carbohydrates. The classification depends upon the number of saccharide units in their molecules, which would be yielded upon hydrolysis. Monosaccharides. Monosaccharide contain 5 and 6 carbon units. Formula would be C5H10O5 and C6H12O6. The functional group present in carbohydrates are either aldehyde or ketone and alcohol. Properties of monosaccharide. They are crystalline solid. They are water soluble. They are sweet in taste, act as reducing agents, and cannot be hydrolyzed further. Oligosaccharides, in which let us take disaccharides. When two molecules of monosaccharides combine, they will form disaccharides. Disaccharides on hydrolysis in presence of acid or enzyme produce two molecules of monosaccharides. So disaccharides can be hydrolyzed. Trisaccharides. 3 molecules of monosaccharides combine and form trisaccharides. They also can be hydrolyzed in presence of H plus or enzyme, and we'll get 3 molecules of monosaccharides. Tetrasaccharides. 4 molecules of monosaccharides combine and form tetrasaccharides. Tetrasaccharides are hydrolyzed with enzyme or an acid, and they will give you 4 molecules of monosaccharide. Stracchose is one of the tetrasaccharide. Polysaccharide. Well, it is a polymer of monosaccharide, which is non-crystalline solid. It is tasteless and insoluble in cold water. But when you take boiled water, it will form colloidal solution. That means it is neither a true solution nor a suspension. Monosaccharides. Now we will focus on monosaccharides. C6H12O6, this is the basic unit of monosaccharide, and there are two main compounds of monosaccharides, glucose and fructose. If you see, their molecular formula is same, only functional group present in glucose and fructose are different. Glucose contain aldehyde, fructose contain ketonic group. They are also known as aldohexose and ketohexose. Glucose. It is also known as dextrose or grape sugar. Preparation of glucose. Well, sucrose on hydrolysis in presence of acid or enzyme gives glucose and fructose. Starch is a polymer of glucose, and therefore on hydrolysis of starch we will get n number of glucose. These hydrolysis occur at 120 degrees Celsius temperature and 3 atmospheric pressure. Now, conformation of structure of glucose. At present, many advanced instruments are available, and because of that, it's very easy to find out complicated structure within few hours. But when those all advanced instruments were not available, no spectra was available, at that time, people tried to confirm the structures of various compounds using their chemical properties. So here we will see how glucose structure was confirmed with the help of chemical reactions. First, glucose reacts with acetic anhydride. Well, when any molecule reacts with acetic anhydride, it may contain alcoholic group, because alcohol reacts with acetic anhydride and produce acetyl derivative. Here we are getting pentaacetyl derivative of glucose, and this suggests that 5 molecules of acetic anhydride are used in these reactions. That means there must be 5 OH groups. So when any molecule which contain OH group, it will react with acetic anhydride. Breaking of acetic anhydride takes place from here, and H will be removed from alcohol. These H plus will transfer to oxygen, and COCH3 group will join with O, and therefore we will get R, O, CO, CH3 plus acetic acid. And this is known as acetyl part or acetyl derivative. So, glucose react with 5 molecules of acetic anhydride. It confirmed that glucose contains 5 OH groups. Reaction of glucose with methyl iodide. This is also very important reaction of alcoholic group, OH. Here, glucose reacts with 5 molecules of methyl iodide, so it removes 5H from glucose and they produce pentamethyl ether derivative of glucose. This suggests that there are 5 OH groups in glucose. Well, on hydrolysis further, this kind of compound which will be hydrolyzed and it will produce tetramethyl derivative of glucose. It suggests that out of 5 OH groups, one OH group is primary and remaining 4 OH groups must be secondary. This indicates that one OH group in glucose is different from other OH groups. So let us see how this reaction takes place. So when any compound which has OH group, alcoholic group, if it reacts with methyl iodide, then again H plus is removed from here. Methyl iodide will fragment like this. Iodine join with H and form HI, and methyl group will join with O and give ether derivative. So we'll get ROCH3 plus HI. And ether can be hydrolyzed by acid, which will again produce OH. So this reaction proves that there are 5 OH groups, but on hydrolysis only one OH group is coming back, not all. That means these 4 OH groups must be different than one. So this is primary, others must be secondary. Glucose reacts with HCN. It gives addition reaction. And this is nucleophilic addition reaction. And the product is cyanohydrin. So it is glucose cyanohydrin. Glucose also reacts with NH2OH, hydroxylamine. It also gives condensation reaction and produce glucose oxime. So these two reactions confirm the presence of carbonyl group in glucose. So the compound which contains carbonyl group gives these two type of reaction. This is nucleophilic addition to carbonyl group, and this is condensation reaction to carbonyl group, and these products are existing. It suggests that glucose must contain carbonyl group. Fehling test. Well, in Fehling test, we take Fehling A and Fehling B solution. On heating A and B, it will produce copper oxide. And this copper oxide is weak oxidizing agent, and it reacts with glucose and produce gluconic acid. In gluconic acid, there is one COOH group. It is obtained by oxidation of CHO. This reaction proves that glucose contains CHO, aldehyde group. Second confirmation for aldehyde is silver mirror test, where glucose is treated with ammoniacal silver nitrate solution, which will produce Tollens reagent, that is complex of silver, and this is again mild oxidizing agent. It can oxidize aldehyde group, and glucose produce gluconic acid once again, and this reaction proves that glucose must be having CHO. So this way, glucose is having carbonyl group, which is aldehyde. Glucose is having alcoholic group, and there are 5 OH groups. Oxidation with nitric acid. Glucose on oxidation with nitric acid, which is very strong oxidizing agent, gives saccharic acid. In saccharic acid, there are 2 COOH groups at the end, and this is 6-membered compound. So it is dicarboxylic acid, and therefore it confirms that glucose must be having one CHO group and one primary alcohol, because primary alcohol on oxidation with strong oxidizing agent can give acid. So this way, glucose confirms CHO and CH2OH group. Reduction of glucose with HI. On reduction of glucose with hydroiodic acid gives linear normal hexane compound, and it suggests that there are 6 carbons in glucose which are linked linearly. So glucose is open chain compound, it has CHO group, it has CH2OH group, it has 5 OH groups. Now reaction of glucose with phenylhydrazine. You know, any compound which is carbonyl and aldehyde or ketone, it gives condensation reaction with phenylhydrazine. So here glucose react with phenylhydrazine molecule. First step, condensation. In condensation, 1 oxygen from CHO and 2 hydrogen from NH2 removed gives H2O, and now we have phenylhydrazone derivative of glucose. Now this molecule again react with phenylhydrazine. This is something different. And here oxidation takes place of glucose. In this case you can see there are 4 CHOH group between first and last carbon. So below this carbon there is 1 CHOH over here, and 2 hydrogen from CHOH will be removed by phenylhydrazine. 1 hydrogen joined with NH2 which will give NH3, and another hydrogen joined with PHNH and gives aniline. That means second molecule of phenylhydrazine reacts with hydrazone derivative and it gives oxidation reaction. And if CH from CHOH, if 2 hydrogens are removed, then we will get C double bond O. So second molecule of phenylhydrazine produce C double bond O group in hydrazone derivative of glucose. Once C double bond O is produced, definitely it will react with again phenylhydrazine. So here we have excess phenylhydrazine. So ultimately 3 molecules of phenylhydrazine reacts with glucose. So third molecule again produce condensation product, because now we have C double bond O in this compound. So 2 hydrogen join with O and produce C double bond N and NHPH derivative. So this is glucose osazone. When there are 2 hydrazone known as osazone obtained from glucose, so it is glucosazone. This reaction confirms that glucose and fructose are functional group isomers, because the same compound obtained from fructose also. From these reactions, glucose is assigned the following structure, and this is known as D-glucose. This open chain structure suggested could not explain the following reactions. Glucose does not react with sodium bisulfite. Now addition reaction with sodium bisulfite is a characteristic reaction of aldehyde group, but glucose does not react. It suggests that glucose should not have CHO group. Skiff test. This is very important test of aldehyde group. Skiff reagent is mainly SO2 with rose aniline dye. So any compound which is having CHO group, that is aldehyde, must react with Skiff reagent, which is colorless solution of rose aniline dye, because it contains SO2. Then this SO2 will be oxidizing agent which will oxidize CHO and produce COOH, and so SO2 is removed from rose aniline dye, therefore we'll again get color of rose aniline dye, and that is magenta color. That means take aldehyde, add Skiff reagent, shake well, and if you get magenta color in the solution, this confirms the presence of CHO group. Well, glucose contains CHO group as we confirmed earlier, but glucose does not react with Skiff reagent, and there is no coloration, and it suggests that there is no CHO group in glucose. This is pentaacetyl derivative of glucose. In pentaacetyl derivative, there is free CHO group, but this compound does not give condensation reaction with hydroxylamine, and it also suggests that there is no CHO group. So this way, glucose gives some typical reactions. Some reactions prove that glucose contains CHO, because it gives Fehling test and silver mirror test. and these reactions prove that there is no CHO. Then what is glucose? So well, only open chain structure was not accepted. Glucose, when it is soluble in methanol, we prepare saturated solution of glucose in methanol and then crystallize it. You will get crystals glucose, and it is optically active. Its specific angle of rotation is plus 111 degree. That means this is dextro. Glucose is also soluble in acetic acid. Prepare saturated solution of glucose in acetic acid and then crystallize it. And on crystallization we will get crystal glucose. Its specific rotation is only 19 degree. So this way, the glucose obtained from methanol solution and from acetic acid solution are different. Optically, they are different because their optical rotations are different. So, these all things cannot be explained by open chain structure. So, the specific rotation of glucose suggests two different types of isomers. Fischer proposed cyclic structure of glucose, which can explain the different specific rotation related to alpha and beta cyclic structure. This is open chain structure of glucose. There are 6 carbon. 5th carbon has CHOH group. Fischer suggested that hydrogen from 5th carbon of OH group will transfer to C double bond O oxygen, and therefore there will be only single bond left with this carbon. So one valency of carbon, one valency of oxygen set free, and therefore these oxygen form a bond with carbon of first carbon as well as with 5th carbon, and this is cyclic structure of glucose. So this is the cyclic structure of glucose. This is oxygen, first carbon which is having CHOH, second carbon CHOH, third, fourth having CHOH, but 5th carbon has CH2OH and H. Well, here the position of OH on second carbon, third carbon and 5th carbon remains same. But second possible structure, cyclic structure of glucose, in which the OH group on the first carbon may be on top. So this way, first is known as alpha D plus glucose. Its specific angle of rotation is 111 degree. And second structure, where the change is only on first carbon, is known as beta D plus glucose. So alpha D plus glucose is having specific angle of rotation 111 degree, and beta D plus glucose is having angle of rotation 19 degree. So this way, both are different. Alpha and beta structures of glucose are known as apimers or anomers because the arrangement of OH group is different only on one carbon, C1. Now, this is alpha D plus glucose. When it is added in water, then hydrogen from this first carbon of OH group again will shift to oxygen, and breaking this bond produce open chain structure, and that is open chain structure and whose specific angle of rotation is 52 degree. And again this can return to the first carbon oxygen and produce cyclic structure. So this process is reversible. From this open chain structure, it is possible that again hydrogen will transfer to oxygen of first carbon, but then OH can shift to the top of this molecule. That means it is beta D plus glucose, whose specific angle of rotation is 19 degree. And it is also reversible and it can produce open chain structure. So this way, alpha D plus glucose in aqueous solution converted to open chain structure, and again open chain structure can be converted to beta D plus glucose, and the whole process can be reversed also. This process is known as mutarotation. When these alpha and beta glucose are dissolved in water, the specific rotation of alpha form gradually drops from 111 degree to 52 degree, while the specific rotation of beta form gradually increases from plus 19 to plus 52 degree. This phenomenon of change in specific rotation ultimately leading to a constant value of plus 52 degree in aqueous solution of glucose. Therefore, this glucose is dextrorotatory, and this change in process in which the alpha is changing to beta and beta is changing to alpha is known as mutarotation. This is known as pyran, and it is 6-membered ring with 5 carbon and 1 oxygen. Well, cyclic structure of glucose are similar to pyran except this double bond, and therefore this glucose is also known as pyranose. So it is known as alpha D plus glucopyranose, and this is beta D plus glucopyranose. Two structures of glucose theoretically, and the change is this carbon, second last carbon. If you put OH group on the right side of the second last carbon, then it is known as capital D glucose. And if you put OH on the left hand side of the second last carbon, then it is called L glucose. Plus sign indicates dextro, minus sign indicates levo, and it is purely experimental. With the help of experiment only we come to know that which one is dextro and levo. But capital D and capital L can be determined theoretically. Specific angle of rotation. This can be determined with the help of this formula. Well, alpha is the actual observed angle, L is the length of the tube, and C is the concentration of the solution. So bracket alpha is specific rotation, T is temperature in Kelvin, lambda wavelength of the incident light, sometimes D symbol is also used for sodium light, alpha is observed angle of rotation by polarimeter, L is the length of the tube in decimeter, and 10 centimeter is equal to 1 decimeter, C is the concentration of compound in grams per milliliter. This should be in grams per milliliter. Let us take one example. Numerical. The observed angle of rotation of 2 gram of sucrose in 10 ml of solution in polarimeter tube 10 centimeter long is plus 13.3 degree. What is the specific angle of rotation of solution? Well, C is 2 grams per 10 ml. So 0.2 grams per milliliter. L is 10 centimeters, so that is 1 decimeter. Alpha is 13.3 degree. Substitute these values and you will get plus 66.5 degree. So this is specific angle of rotation of sucrose. Fructose has ketonic group, and this ketonic group is on second carbon, and it is having OH on the right hand side on second last carbon, so it is D minus fructose. It is white crystalline substance, soluble in water, partially soluble in alcohol, insoluble in ether, sweet in taste. This compound is furan. It is 5-membered ring, 1 oxygen and 4 carbon. When cyclization of fructose takes place, then because ketonic group is on second carbon, the hydrogen from 5th carbon of OH will shift to C double bond O, that means second carbon, and therefore it will form 5-membered ring like furan. So fructose is known as alpha D minus fructofuranose or beta D minus fructofuranose. This is Fischer projection, and these are Haworth's projections.